slide past you here.
You know, the reception is terrible in the math lab.
All right, let's get started. I don't have your take-homes done to hand back. Just didn't have enough time, so I'll have those for you next week. I try and get them done by Friday, so I'll post the grades online. Hopefully you aren't in too much of a hurry to get those grades. On the next mini exam that I handed out last time, I've had some questions about, is it as straightforward as it seems? And it is as straightforward as it seems. But just make sure that since it is very computational and very mechanical, that you are paying attention to your derivatives, double checking your chain rule and things like that, because that's what I'm going to be looking for, accuracy, okay? And that's it. We're going to move on. So we're in 11.6 now. We finished up chain rule last class. And this section is entitled The Directional Derivative in the Gradient Vector. So I'm sure you all remember the wonderful demonstration that I did when I got up on the chair, right? And I was trying to point myself in certain directions, right? And what we had basically was a surface, right, a function of two variables. And we said when we're standing up on the surface at a point, we could point in a direction that would be parallel to the x-axis, right? And that slope of that line would be our partial derivative with respect to x. And then we could point parallel to the y-axis, and that would be our partial with respect to y, right? Yes? But we also had kind of talked a little bit about, well, why point that way or this way? There's actually an infinite number of directions I could have pointed, right? And that's what today is about. The directional derivative is a more general version of what we've already done. It allows us to point in any direction as opposed to just parallel to one of the coordinate axes. So to start, we're going to take a look at this visually first. So let's see how this works out. We recognize this is a surface. Can you all kind of see this surface here? Yeah? Okay. And it's actually f of x, y equals sine of x minus y plus cosine x. So there it is. There's that sheet that's floating in the wind, right? Well, it's not moving. It's actually, but the idea is that it's some surface up here. And I'm actually at a point right here. So that's a point up on the top of the sheet. And if I look at this straight down like this, okay, then this is my x-axis, this is my y-axis, z is coming out at us, right? And I want you to notice that below this point, directly below it, down on the domain, right, on the xy plane, I have that red point. And right now that red point is pointing, right? I have this point, I have this arrow, this is pointing down the x-axis, right? So if we were to sit there and ask ourselves to find the slope of the tangent line as we are pointing parallel to that red vector, we'll call it a vector, then what we're doing is we're holding y constant, right? And we're slicing this thing through, creating the curve, and then finding the tangent line, which is this, I don't know if you can see that, but it's that blue line, right? And that's what that partial derivative, oh, it's not showing up over here. It's okay, don't worry. But that's what that partial with respect to x would be, yeah? Now, if we change it and we run parallel to the y-axis instead, what I'm going to do is I'm going to rotate this vector and point it out to the y, right? So let me do that now. There we go. So I've pointed out the other direction. You all agree? I can slice it the other way and find the tangent. That tangent line isn't showing up very good, but y'all see it? Okay. So let me go back to the other one because it seemed to work better. There it is. Now, today, what we're going to do is we're going to use this arrow and we're going to just rotate it arbitrarily. So let's see what happens if I take that arrow and just start, well, oh, I'm doing the wrong one, sorry. This one. So you see it? See how this spins around like this? And wherever I want to stop it, I can stop it. And once I stop it, I have another graph that's cutting through the curve, and I have another tangent line. So for every direction, I have some tangent line, don't I? And our goal is to try and come up with a way of having a formula that would represent that slope. Got it? No questions on it geometrically? All right, so what are some things I said to look at? We can pick any point in the domain to get a point on the surface. So back to this picture. I was at the origin here, wasn't I? I was at the origin, that's where I was. But I could go to any place. I could go to another place on the surface if I wanted to. All right, so I could go over here, kind of on this front edge of the surface, and I could cut through that with the plane, get the tangent line, and spin that thing around, right? Yeah? So what I want you to see from this view, if I'm spinning this around, that red vector, I didn't move it. So if I look at this from the top, do you notice that my plane, I'm going to rotate a little more. Damn it. There we go. Notice that the plane that's cutting through the surface at this point is parallel to this, right? Okay, so this is a vector. We could imagine you could slide that vector over underneath this. I didn't do that. I could go back into the code and redo it and have it do it, but I just left it at the origin, all right? All right, so we can find this, all right? We can pick any point in the domain to get a point on the surface. At that point on the surface, we can pick any direction we want. In that direction, there is a tangent line. The slope of that tangent line depends on the direction that we're pointing in. That's what we know so far. Where's my formula? I was like, where the hell's the formula? We need the formula. All right, there we go. So here it is. This is the Big Daddy formula for today. And I'm going to write it down on the board over here so that we have it. So I don't have to keep referring back to it. By the way, the homework assignment for last class for the chain rule, I never gave you the homework assignment, but I emailed it to you today. And the homework assignment for this section, I did the videos for the homework today, so they're already up on YouTube. And the assignment for this is at the end of the notes. So this is the formula. Let's talk about this. All right, this capital D tells you that we have a derivative, right? That was one of the notations. So this is the derivative. Right, so if z is a function of x and y, so we've got this surface, then the derivative of the function f of xy in the direction of u. Okay, so this u subscript tells you the direction you're pointed in. Do you remember when we did this notation? Like, we never used it. I showed you all these different notations. But wouldn't this mean, oops, sorry. Sorry. Wouldn't this mean the partial derivative with respect to x? Which means point in the direction parallel to the x-axis, right? So this x actually was telling us the direction. We weren't really looking at it that way. This is telling us the direction is going to be u, which is going to be a vector. It will be equal to a times the partial, this is times the partial of f with respect to x, plus b times the partial of f with respect to y, where a and b are the components of the vector in the direction we're pointing. So we just need to know what direction to point in. But there's one huge thing you have to be careful with. The direction vector that you use for this formula, the u, must be a unit vector. It has to be a unit vector for this formula to work. If it's not a unit vector, then you have to make it a unit vector. And how do we make unit vectors out of vectors? Divided by its length or multiplied by the reciprocal of its length, right? So we know that if someone gives us a direction, we can always find a vector in the same direction with unit length. Now what's really kind of nice about this formula, before I get to this example that's coming, and I'm going to make this smaller now. That's too small. Can you read that? Yeah. Okay, so what's nice about this is what if I gave you a unit vector? Well, you can tell me if this is a unit vector. What if I gave you this direction? So I'm not doing this problem right now, okay? I'm just asking you to think about this. Is that a unit vector? Yes, okay. What direction is that pointed in? So think about domain-wise. If you're just looking at the ground, you know, here's your x, here's your y. This is just the domain of the f function. This is the vector I hat, right? Which just points out to the right. So it's pointing in this direction, like this. And if I'm pointing in that direction, isn't that exactly the partial derivative with respect to x? Well, let's see what happens in our formula. If we go and use that formula over there, do y'all see what's going to happen? What's a for us? 1, so you get what? Partial of f with respect to x at xy plus, now what's b? 0, so 0 times partial of f with respect to y at xy. This is gone, and it's just the partial of f with respect to x, which is what it should be, because I'm pointing in the x direction, yes? Similarly, if I used a different direction vector, like, I don't know, j hat, then I would be pointing down the y-axis, wouldn't I? And it should be, that should correspond to the partial with respect to y, which it would, right? Because this would be 0 now in front, and this would be 1, right? So do you see that this is just a more general formula? In the event that we're pointed down the x-axis, it still works, or the y-axis still works, but it works for all directions. All right. So let's do this problem. If z is equal to f of x, y is equal to x cubed minus 3xy plus 4y squared, then find the directional derivative at the point 1, 2 in the direction of a vector making an angle of pi over 6 with the x-axis. All right. So let me look real quick, at the domain. Here's a domain of f, which is the flat ground, right? That's the ground, just looking at it from the top. So here's x, here's y. I'm going to the point 1, 2, so 1 for x, 2 for y. And that point's getting plugged into the function, right? So three-dimensionally, it looks like this. Here's x, here's y, here's z. Going out 1 on x, 2 on y. So something like that, right? That point, agreed? That's being plugged into the function, which is sitting, what, it's a surface? It could be below, right? It could be, but let's just, for the sake of making this easier to look at, let's just say that that surface is sitting above us, up here somewhere. Here's my little surface up there. And I am plugging this in, and I should be somewhere on this surface, right? Somewhere on there. There's my point. Now what I want to do is I want to point in the direction of a vector making an angle of pi over 6 with the x-axis. So come back over here to this domain. Imagine a vector that starts at the origin and has an angle of pi over 6 with the x-axis. Pi over 6 is 30 degrees. So it's pointed in this direction like that, right? I want to take this point, I want to go up to this function, which means go up to there, and be pointing the same direction as that. Do y'all follow that? And then from there, figure out what the slope tangent line is. So that's going to be kind of hard to draw the pi over 6 here, but I think it would look something like this on the ground, wouldn't it? Y'all kind of see that on the ground? Okay, so I just need to come up here to my function. and I need to kind of point in the same direction. Kind of hard to do, too close to the board. I need to point in the same direction as that vector. That doesn't look like the same direction, does it? It's hard to do, but you get the idea, right? And just imagine if I'm standing there pointing in that direction, and I take a step, right? Am I going up or down? If I'm going up, by how much? If I'm going down, by how much? And that's what this derivative represents. It's an instantaneous rate of change at that point on the surface. Yeah? Okay. So it's a directional derivative. So we're going to need to use that formula. Do you think that you'll be able to find the partial of f with respect to x? We'll need that, right? Because it's in the formula. We can do that, partial. We can do the partial of f with respect to y, no problem. All we need to figure out is what's u. What is u? And u has to be a unit vector that points in the same direction as that vector right there, the red one. So how are we going to get u?
Make a vector out of 1 and 2 and then multiply.
Be careful. This 1 and 2 has nothing to do with the direction we're pointing, right? The 1, 2 is just where we are up on the surface, right?
Use trig.
Okay, you can use some trig here, couldn't you? Let me see. I'll leave this up here. How about I use this? How about the unit circle? Don't we love the unit circle? Somewhat. Pi over 6 is right here. And that corresponds to an actual point that we all should kind of remember from pre-cal. This was a common angle, wasn't it? This is root 3 over 2 and 1/2, isn't it? So if I have an angle of pi over 6 with the x-axis, that corresponds to that point on the unit circle. And of course, I can make a vector out of that point, couldn't I? Just turn this into a vector, and that's going to correspond to the direction I want to point, right? So how about that as a candidate for you? How about root 3 over 2, 1/2? Now, it has to have unit length. Is it a unit vector? Well, it came from the unit circle, so it should have length 1. But you could double check it, right? You could just take its magnitude real quick. What's the magnitude of this? Square that. 3/4, square that. 1/4, 3/4 plus 1/4 is 4/4. That's 1, take the square root. So yes, it is a unit vector. Okay, so that's it. We have everything we need. This is A, this is B, and we just go to the formula. Well, we never took the partials. Why don't we take the partials next? I'm trying to preserve as much room as I can up here. Let me do the partials right here. What is the partial derivative of f with respect to x? 3x squared minus 3y, and that's it, right? Yes? All right, so 3x squared minus 3y, and then the partial of f with respect to y, which is minus 3x plus 8y, right? So that's our partial. Those are our partials, and now I'm going to go over to that formula over there, right? And I'm just going to start plugging things in. I guess I have to erase this pretty drawing. So the directional derivative in the direction of the unit vector u of f of x, y should be equal to a, which is root 3 over 2, times the partial of f with respect to x, which was 3x squared minus 3y, plus the b, which was 1/2, right? And then minus 3x plus 8y. And that's it. That right there is the partial derivative, right? Sorry, the directional derivative of the function if I'm pointed in the direction of the unit vector u. And this will work for any point you give me now. So if I go to any point on the surface and point in the direction of u, this is going to be my tangent line. So now let's go to the specific point that we're talking about. which is the point 1, 2. So see, the 1, 2 really doesn't come in until the very end. Right? And now this is just plug and chug, right? So 3 minus 6, I believe, plus 1/2, negative 3 plus 16. Check my math. I'm working fast here. Negative 3 root 3 over 2, and then over here, 13 plus 13/2. So negative 3 root 3 plus 13 over 2. Anyone else get that? Yeah? That's it. That's a number, right? And I'll get my calculator out just to see. I'm curious, like, is that a positive or a negative number? I guess we'd have to check, huh? Is it, this whole thing's 3.9, approximately? I'm trusting your calculator skills there. Can I get a second? Any 1 second? Not that I don't trust you, but I always like to have at least 2 people confirm. It's not that I don't trust you. It's I don't trust you. Sure. Yeah. It's less than 2, greater than 1. Yeah, yeah. I don't know. I don't have memorized. So, yeah, no. Yes, okay, so that's it. So that means if I were to be standing on that surface at that point up there, pointing in that direction, and take a step, I'm going to be going up, right? Now, if I turn around and go the opposite direction, what do you think is going to happen? If I turn around like 180 degrees? It's going to go down because, you know, if you're going up this way and you turn around, you're going to have to go down. So, all right. Questions?
If you have, could you draw the triangle? Could you draw a triangle just for my question?
You want me to just draw a triangle?
A random triangle. And then for your height, for 1. All right, triangle.
Oh, okay, that's a spherical triangle. It's a triangle on a sphere. We'll talk about that later. So you mean like a Euclidean 2-dimensional triangle, like this? I'm being a smartass, I'm sorry.
When I think of sine of 30 degrees, I think 1/2, and then I put 1 for the height, 2 for the hypotenuse.
Mm-hmm.
And then you can put root 3 for the, I guess, the x.
Yes, you could do like a right triangle like this and then say 1 and 2 and then root 3. Is that what you're saying?
Components, could you do root 3 and then 1 instead of root 3 over 2 and 1/2? Is that still unit length?
Could you use what instead?
Saying to multiply everything by 2, basically.
You have to divide it by 2.
Could you,
Like,
could you use root 3
would that work for
and
you?
1
Could you-
as your u?
would
No,
work?
that would not work.
It would.
No, because this is not a unit vector. Yep. So what you have to have, yeah, your hypotenuse would have to be 1. But what you could do real easily to fix that is just find the length of this vector. So, you know, find its length. Take the square root of each of these pieces squared. So square that, you get 3. Square that, you get 1. Square root of 4 is 2. And just divide each by 2. And now you have a unit. Well, that's what we had before, yes. So you would be off by a factor of 2 had you not normalized it and made it unit length. Got it? Okay, let's look at the next one. Or the next idea here. I shouldn't have been a smartass, I'm sorry. But it's interesting, you know, spherical triangles don't have the same properties that the ones we're used to have. All right, so z is equal to f of x is equal to natural log of x squared plus y squared. Find the directional derivative at the point 2, 1 in the direction of the vector u is 1, negative 2. So this is a little different in this problem because in the last one, told you that we gave you the direction by giving you an angle and how that angle was relative to the x-axis, right? This one, you're not given an angle. You're actually just given a direction vector, right? So I'm going to go back. I'm going to draw the domain again. The point that I'm at is 2, 1. The direction vector, which is completely separate from the point, right, has nothing to do with the point, is the vector negative 1, 2. Can y'all see the surface above this? Can y'all see the surface that's above this thing? And we're up at a point on this, and we just want to be on this surface pointed parallel to that red vector, right? And then you just turn the whole thing over, and now we're, the surface is up. Okay. So we need a couple of things: partial derivatives, which we should be able to take, right? And we need to figure out what our u is. U is given to us, or is it? It's not. It's not a unit vector. So we can't call that the u. Even though I called it u here, I'm trying to trick you. All right? So this is not a unit vector. So I'm going to call a new vector v, that u vector divided by its own length. And then what I'm going to do is in my formula, I'm going to use directional vector, directional derivative in the direction of v, because v will be a unit vector. So we just take the vector u and then divide it by its own length. What is the length of u? Square root of 5, right? So I'm just going to divide it by its own length. But that just means you divide each of the components. And that's it. Yes, you could rationalize, but I'm just going to leave it like that. So this is a and b. We agree with that? All right, so I need some partials. Let me get some partials right now before I start putting this all together. Partial with respect to x. 2x over x squared plus y squared. So derivative natural log of something is 1 over it, and then, okay, partial with respect to y is 2y over x squared plus y squared. There we go. And now I'm ready to put it all together. So I'm kind of going a little quicker here with these partials because that's now in the past, okay? The directional derivative in the direction of v of the function at some point xy should be a, right? So negative 1 over root 5 times the partial with respect to x, which is this, 2x over x squared plus y squared, and then plus b, which is 2 over root 5, and then the partial of f with respect to y. Is it doing that again? I hear that every single time. See, I've got the magic stick. Is that what we called it last time? All right, so that's it. That's our formula, right? And then now we just need to plug in 2, 1, and we're done. So let's plug in 2, 1. Are there any questions? Does this seem straightforward? Yes? No? For now, I mean, we don't want to make this more complicated. The only thing that's going to get complicated perhaps in the homework is maybe these partials are going to suck a little bit. We haven't talked about yet, what happens if we have like a function of 3 variables. Like, can we still do a directional derivative? Does it even make sense? So we'll talk about that in a second. All right, what happens when I plug in 2, 1 for this right here? 4 over 5, 4/5. And then when I plug in 2, 1 on this one, what do I get? 2/5. And then adding these, they have the same denominator, don't they? Uh-oh.
Yeah, I got 0.
You got 0. Did we mess up? This is a number. It's not a vector. What does that mean? Flat. You're flat. So you're standing, and you might possibly be at the top of like a hill, or possibly the bottom of a hill, or neither one. It could be a saddle point. It could be a lot of different things, okay? Because the surfaces are complicated. It's not as simple as, back in Cal 1, your derivative in Cal 1, right? If the derivative was 0, you were either like here, right? Or you were here, or you could possibly have had something like this happen there, like this, right? Like that was pretty much it in Cal 1 when the derivative was 0. You were either at the top, at the bottom, or at one of these weird points like this where you're neither the top nor the bottom. This is kind of like what a saddle point is for us, which is later. But it can be even more complicated with surfaces. So it's okay to have a derivative of 0. The next section, in fact, is about trying to find the maximums and minimums of a function of two variables. It's a method, it's a procedure on how we do find the highest and lowest points on surfaces. And do you remember, like in Cal 1, we had like the first derivative test and the second derivative test? We have something like that for surfaces also. And then we say, hey, we can do a pretty good job with that. And then we get into the next section, which is 11.8, which is called Lagrange multipliers. And that's an even more specialized version of finding maximums and minimums. And that section is kind of tough. But your test is a week from this upcoming Monday, right? Your midterm is a week after that. So we will have, next class we'll do 11.7, okay? And then we will, on Wednesday, do more 11.7, start 11.8. Then the following Monday will be your test. It'll only cover up through 11.7. I'm not going to test you on 11.8 until the final. All right? And maybe next Wednesday we'll have some time to talk about the midterm. Making a midterm is kind of hard because we have a lot of information, right? So how do I pick something that's going to fit in an hour, 40 minutes? I don't know. I guess that's the pleasure I get to have, is trying to pick something to fit in an hour, 40 minutes. And you have the pleasure of preparing for something that is going to be an hour and 40 minutes and can cover, almost 8 weeks of class. So it's a good thing. It's a good exercise because a lot of times as you get higher in your education, there's going to be less tests. It's going to be more like midterm final. I took plenty of classes where my grade was 50% midterm, 50% final. And for an hour, 40 minutes, you had to walk in there and perform. And you had to be ready for it. There wasn't any after the test like, hey, can we do corrections? Or like, can you curve us?